Okay, so let's talk about some basic things we need to do to validate a given regression model. Recall our example. When we use only size to predict price, our regression model is this one. But when we add the number of bedrooms, we have another formula, right? So it must be the case that some formulas are good, some formulas are bad. Or say it in this way, in general, for a given regression model, how may we evaluate its overall quality? We want to know how good it is, how much it can explain or it can help us predict why, how large would be the possible errors. Okay, so we want to know this. Suppose that we do not do regression, then we would very naively estimate yi by what? By the sample mean. Okay, so that means I give you a set of data. Okay, good. And then you calculate the sample mean, which is the average price of the 12 houses. And then how would you predict the next house? I give you the size, but you just ignore it and randomly guess that the next house, the price would just be the average price. Okay, you can see that this idea is very bad, and in some sense we cannot do worse than that, because we have no model to do the prediction, and we have information for x, we have the size information, but we completely ignore it. So it just cannot be worse. Okay, this is the worst idea, the worst way to do prediction. So now we want to know how much does our regression model do better than that. Okay, this comparison can help us to understand how good our regression model is. If this and the very naive way are somewhat the same, well, then our regression model is useless. But if this is much better than that, then we're good. So without a model, we define something called the sum of squared total errors, which is this one. Okay, for each yi, we estimate it as y bar. So there is a difference. There can be squared, and we sum up all of them. That's SST. With our regression model, what we do is SSE, right? For each yi, we estimate it as y hat I according to our formula. So, given that, we can calculate SSE, sum of squared errors. Then we compare these two numbers. SSE cannot be larger than SST, right? Because this is so stupid. SSE is better. So this number is smaller. So we can have this ratio. This ratio must be smaller than 1. Okay? If SSE is very close to SST, our regression model is useless. Then this R² value would be close to 0. On the other hand, if SSE is much smaller than SST, then this ratio would be small, our model is good, and the R² would be close to 1. So we are going to use this formula to define this value R², and the larger R², the better the regression model. And it has the physical meaning. The physical meaning is that R², this number, tells us what's the proportion of total variability of our dependent variable that can be explained by our regression model. Okay, it may be 60. That means 60% of the variability can be explained by our model. 40% are still random noise that we cannot control. If R² is 80, that's even better. 80%. That's even better because only 20% are random noises that we cannot explain. So the larger the larger x², the better the regression model. So whenever we find the estimated coefficients, then with the formula we introduced in the previous page, we can calculate R². So there is no reason for us to do that by ourselves. Statistical software always includes R-square when they generate the regression report. Okay, something we will get for free. So for our best regression model with size as the only predictor, we have R-square to be around 53%. That means around 53% of a house price is determined by its size. Okay, there are other determinants of the house price, but at least house size is pretty important. Okay, so that's something we know. So now this way allows us to know how good our regression model is. We want R-square to be large as possible, as close to 1 as possible. In practice, if you have R-square that is around 60, 70, or 80%, that's very good. Even 40% or 50% in many applications are still treated very good. Okay, because the practical world is very random. There are a lot of things that we cannot control, especially if we are doing business, if we are dealing with people. Okay, so 40%, 50% can be very good regression models. For other applications, then this criteria or this threshold may be different from application to application, so it depends. For different industry, a good R-square can be different. Okay. One may be wondering what's the difference or what's the relationship between R-square and R, the correlation coefficient. And indeed, R-square is the square of the correlation coefficient if we only have one independent variable. When we have one independent variable, we can calculate the correlation coefficient between the dependent and independent variables. Okay? And we know that some number between -1 and 1. So it's not very surprising that R square is our R square. Okay? But we use a different symbol for capital R because R square is actually defined for any number of independent variables. So it's much stronger or much more general than correlation coefficient. Okay, but originally it comes from the correlation coefficient when there is just one independent variable. So that's why its name is called R square. Okay, R square can be used to judge one model. Then naturally it can be used to compare multiple models. For example, for our two variables, size and bedrooms, we can do 3 combinations. We may either use size only, use bedrooms only, or use both of them. We can see that using size only is somewhat good. If we only use bedrooms, well, R-square is much smaller. So that means size is more important in determining the price. Bedrooms has some impact, but not so strong. If we include both of them, we have a largest R square. But it's dangerous here because if we compare these two numbers, we probably feel that having both variables gives us the best regression model because its R square is the highest. But actually, this is not the case because adding more variables can always increase R square. Why is that? If we compare this model and that model, in this model we have 3 coefficients, beta 0, beta hat 0, beta hat 1, and beta hat 2. Right? When we want to adjust the 3 values to minimize the total sum of square, then what's going to happen? In the worst case, we can set beta hat 2 to be 0. Then we go back to the size only model, and then we can still do as good as the size only model. Then if we are allowed to adjust the beta hat 2, of course we will do better. Okay? So intuitively, When you have more variables, you must explain more variability of your dependent variable. Okay, so that compare is actually not fair. And also, we know that when you include a lot of variables, some may actually be meaningless. So we need to do a few things. First, we need to perform a fair comparison and to identify those meaningful factors. Okay? And if we want to do that, we need to somehow adjust R-square based on the number of independent variables. When you use more independent variables, your R-square must increase. Then we need to adjust the R-square based on the number of independent variables you use. So how to do that? The standard way is to consider the adjusted R-square, which is defined as a function of R-square. N is the sample size, and the K is the number of independent variables used in the model. So that means if I use more independent variables, my R-square adjusted will be smaller. So for our example, if we use size only, our adjusted R-square is around 48%. If we use both variables, adjusted R-square is actually smaller, it's around 45%. So we will say that, okay, using size only is actually better because its R-square adjusted is higher. So that's the idea. When we want to compare different models with different number of independent variables, using adjusted R-square is a better idea in general. Now, the last thing we want to do to validate our model is to talk about the significance of each coefficient. What does that mean? Recall our model with two independent variables here. We actually want to know whether 2.8 and the negative 15.7 are good estimates of our parameters, okay? Because they are just calculated based on the sample. We want to know whether beta 1, okay, this number, and beta 2, that number, whether the two coefficients are really close enough to these two numbers. Or more precisely, what we want to do is to ask whether they are really not zero. Okay? If the two numbers are zero, in fact, in the reality, in the hidden fact, if beta 1 or beta 2 is zero, then that means that variable really has no impact to y, right? So we need to test them. We need to form a hypothesis testing to test whether beta I is zero. If we plug in numbers and see that our beta hat I is somewhat close to zero, then we will be unable to reject H0. We will have no way to conclude that beta I is positive or negative. On the other hand, if beta I hat is quite different from zero, then we probably can get a strong evidence showing that beta I, the parameter, is not zero at some given significance level. Okay, so this is just like testing the population mean or something like that. We want to ask whether that number, whether that parameter is not zero. If we have a strong evidence, then we say it's not zero. Then we can conclude that this variable is really useful in explaining, in affecting the dependent variable. So we look for a strong evidence to show that beta I is not zero. Here, beta hat 1 is 2.8, beta hat 2 is negative 15.8. Okay, this number is obviously larger than that. But as you know, that does not mean beta 1 is close to zero or beta 2 is far from zero, because we need to really test them. The standard deviations or some other related things also play a role. So eventually we can do that. So let's see how. The testing result is actually provided in regression reports. For each coefficient, we would get typically 4 columns in a regression report. Different software may have different formats, but most likely we will get these 4 columns. The first column gives us the estimate values, okay, 2.8, negative 15.7, some numbers we see in the formula that can be calculated by the least square approximation. And then we have something called standard error, which is the standard deviation of the sample mean, something you know that is required, something related to sigma over square root of n or s over square root of n, something we played with when we were doing hypothesis testing. Also, we have something called t-stat. If you check these 3 columns, you would realize that t-stat is coefficients over standard errors. Okay, this divided by that gives you the t-statistics. And that's not very surprising because t-stat is calculated as x bar minus mu divided by s over square root of n, which is exactly the coefficients divided by square root of standard error. And given the t-stat, you're going to perform some t-tests. Why t-test? Because you do not know the population variance. Okay, so given these numbers, you do t-tests, and whether this number gives you a significant result depends on the p-values. Okay, these p-values have been multiplied by 2 because every time when you do a regression, you are doing two-tailed test to test whether beta is 0 or not. So all we need to do is to simply compare these numbers with alpha. Okay, this guy is less than 5%, so in many cases we say it's significant. However, for bedrooms, this p-value is very large, so we do not have a strong evidence showing that bedrooms has an impact. Okay, so if we are using 95% confidence level, then we say we have confidence belief that beta 1 is not 0. House size really has some impact on house price. On the other hand, at 95% confidence level, we cannot conclude that beta 2 is not 0. So we have no evidence showing that bedrooms has an impact on house price. Okay, that's the idea. So every time when you do a regression model, you're going to get a report like this. Then we can check their p-values to see whether this variable is significant or not. You don't really need to worry about these 2 columns. So you don't need to know how to calculate them. You don't need to know how to interpret them. But you need to be able to interpret p-values. Okay, p-values. Here you see 2 stars because we use stars to label p-values. When it's less than 0.1, we give it 1 star. When it's less than 0.05, we give them 2 stars. When it's less than or 0.01, we give them 3 stars. So when you see stars, congratulations, because this variable is significant. You have identified one reason for prices to be high or low because of the size. Okay? If you only use size as an independent variable, you're going to see its p-value to be very small. Okay, then we again have quite confident that it has an impact, especially if you only include it as a single independent variable. Okay, so that's something about model validation. Thank you.